So I'm going to start sharing my screen. Okay, so welcome everyone to Neuromatch Academy Deep Learning Course 2023. I'm going to give a short introduction of myself. So my name is Kiilu. I am a machine learning researcher. I am also a master's student in machine intelligence at AMI. My current research work is in natural language processing, NLP, for low resource languages, where I am currently being advised by Machine Head of Google Research, so the brain team. I'm also a volunteer with Neuromatch Academy as a deep learning curriculum content reviewer. So for today, we have 2 tasks. And without wasting much time, I'm going to go direct to our first task. So our first task is on autograd, and we are going to discuss why this is important for us. So as you know, modern neural networks can have millions or billions of learnable parameters. And training this neural network consists of 2 phases. So the first phase is called forward pass, and is a straightforward one, and involves computing the value of the loss. And the second phase is called backward propagation, and this one involves calculating the gradient of the loss function with respect to the weights in order to update the weights and also minimize the loss. So what I can say is that the backward propagation is just nothing but a fancy name for the chain rule that we have already seen. So in simpler terms, the autograd is just an automatic differentiation engine that powers training of neural networks. So this allows the computer to automatically do the differentiation for you and also to construct the computational graph. So the autograd is implemented in PyTorch and also in JAX. But for our task and for assignment, we're only going to concentrate on the PyTorch. So now we can move on to our next task. And this is on building a computational graph. And this is going to be a practical exercise. And now I'm going to take you through the solutions. Now, but before I do this, I think it's important I take you through this simple graph. So in our case, X is our input and Y is output. This is the true labels. These are the labels that we are going to predict. And also we have W and B, and these are the learnable parameters. And we are going to use these learnable parameters and X to calculate the prediction, the model predictions. And the difference between this prediction and the true labels is what we are going to call the loss. So now let's go direct to the solution. Now we can discuss the code. So this is a class, and we are going to call this class a simple graph for implementing this simple computational graph. And as we have seen, W and B are the learnable parameters. And in PyTorch, to show that these are learnable parameters, we are just going to set this optional argument requires grant is equals to true for W and B. And now we can go direct to the forward pass. And this forward pass takes only 2 argument X and this tensor. So we are going to, this is how we are going to implement it. And then we are going to return the predictions. Now, the next thing that we are going to do is we are going to calculate the loss. And in our case, the loss is L2 norm. That is the squared loss. And what we are going to do, we are going to have calculate the difference between the true labels and the model predictions. Then from the square of these differences, we are going to get the loss. So how are we going to do this in PyTorch? We're just going to take the difference between the true labels and also the predictions, and then we are going to square them, and then we are going to return the loss. So this is what you are required to do to calculate the loss and also to do the predictions. So now that we have the prediction and we have the loss, let's try to run the code and to see what happens. So I'm going to run the code, and then this is the result. So now we see the initial weight was negative 0.5, and the initial bias was 0.5. And the model predicted 0.0, but the true label was 7. And this means that we made an error of 49. So thank you very much. I hope you enjoyed the class.